In this example, we calculate the adiabatic temperature for a reactor where we have 30% conversion. So the idea is we're feeding, in this case, 1 mole of NO, a half mole of oxygen, and they're at 100 degrees C. And what we want is, what's the adiabatic temperature if 30% of the NO is converted, with this being the reaction that we're interested in. So we've already calculated the heat of reaction from heats of formation at 25 C. And we're given simplified forms of the heat capacity just to make the calculations a little easier to work through, less numbers to deal with. So they have a temperature dependence, as indicated here, where the temperature in these equations is in Kelvin. And so the first thing we do, of course, is to make a diagram of the process. And so the system is this adiabatic reactor. We've labeled the feed conditions. We have NO, O2, and NO2 all leaving since we only have 30% conversion. And the unknown is the final temperature. And so we want to set up what's the approach we use to solve this type problem. So what I'm going to do is draw a representation to help visualize the solution. We have 1 mole of NO, a half mole of O2. It's at 373 Kelvin, so I've converted the absolute temperature. And we're going to end up with, if we're converting 30%, then 70% of the NO is unreacted. And likewise, since the stoichiometry is, in this case, 1 mole of NO reacts with a half mole of O2, then we have 0.35 moles of O2. Namely, when 3/10 of a mole of NO reacts, half of that, 0.15 moles of O2 reacts, and so 0.5 minus 0.15 gives us the moles of O2. And then we form 3/10 of a mole of NO2. The temperature is what we don't know. And what we're going to do to solve this is just use the idea of state functions. So what we're going to calculate first is if we cool down this feed to 298 Kelvin, namely 25 degrees C. So we cool down, there's going to be some enthalpy change, delta H1 for that process. Then we'll carry out reaction at 25 C, and we're doing that because we know the heat of reaction at 25 C. So delta H2 is carrying out reaction. And so we've listed the products now of reaction for 30% conversion. So remember, this is 30% conversion. And then we're going to take these products and heat them up to the final temperatures. We'll call that delta H3. And our actual process, we'll call this delta H4. And delta H4 is equal to 0 because it's adiabatic. And so the state function says delta H1 plus delta H2 plus delta H3 equals, and so we change 4, which is equal to 0. So let's look at delta H1. We're going to look at the heat capacities, temperature change. So we're going to start at 373, and we're cooling down to 298. And we have 1 mole times the heat capacity of NO plus a half a mole times the heat capacity of O2. And integrating that gives us the enthalpy change going from 373 to 298. So we were given the heat capacities, and notice these were heat capacities divided by the gas constant. So I've substituted in the heat capacities for NO, for O2, with the half a mole of O2, and then the gas constant is here times dt. So we can simplify this and do the integration. So done is add up the first term, do the multiplication, bring the R outside. We'll do the calculation in joules per mole. And then we've done integration here with these limits. So then we need to substitute in the limits. So this T final minus T initial, 298 minus 373 is the minus 75. And then we have these values squared. We do the calculations, we end up with delta H1 minus 3.42 kilojoules. It's negative because we're taking energy out to cool down. Now the next term, delta H2, is due to the reaction. It's 30% conversion, so we have 30% of the heat of reaction. That, remember, we have at 25 degrees C, so this is minus 57 kilojoules per mole. We're reacting 3/10 of a mole, so this is minus 17.1 kilojoules. And then the third term, delta H3, is very similar to delta H1 with just more species, so it won't go through in as much detail. So now we're integrating from 298 up to 373, so this is going to be a positive term. Heat capacity of NO, 7/10 of a mole. Heat capacity of oxygen, 0.35 moles, and then 0.3 of a mole of NO2 and its heat capacity. So only difference now when doing this integration, it's not to 373 like previously, but it's to our final temperature, and we don't know the final temperature. So up here, again, this should have been the final temperature, and so we're going to end up with an expression after we do an integration that still has the final temperature, the adiabatic temperature we're interested in, and it's squared here. Divide it by 1,000 to convert it from joules to kilojoules so we can use it with the other terms. And then what we're going to do is say delta H1 plus delta H2 plus delta H3 should add up to 0. So substituting in the values for delta H1, delta H2, delta H3, we calculate it and just adding them together, we get this equation, which quadratic equation we can solve for the final temperature. And so the adiabatic temperature is around 720 Kelvin for this problem where we have 30% conversion. It's certainly higher than our starting temperature as we'd expect for our exothermic reaction. And what we've done is take advantage, remember, of state function to calculate the temperature here, because adiabatic means delta H is 0, and we've just added up these three delta H terms in this calculation.